I want you to picture something for me. Imagine you have this heavy steel safe.
Okay, a Spiel safe.
Yeah, and inside this safe is the most sensitive, highly classified document you can possibly conceive of.
Right, like the ultimate secret.
Exactly, the ultimate secret.
It is?
Now, you take this heavy safe and you just hurl it into a massive roaring bonfire.
Right.
And you stand there, right? You watch the metal warp and glow red hot. You watch the paper inside combust, sort of curling up into black ash.
And then the smoke billows up the chimney and, vanishes into the night sky.
Right, so to your eyes, to human perception, that document is gone. The information is physically, irrevocably destroyed.
But here's the thing about the fundamental laws of physics.
Huh.
They actually disagree with your eyes.
Right, because according to quantum mechanics, if you possessed a theoretical supercomputer of unimaginable power, you could painstakingly track every single microscopic molecule of that smoke.
Every wandering photon of light, every scattered particle of ash.
Yeah, and you could run the laws of physics backward. You could reverse engineer the exact ink on that paper.
Because the information still exists in the universe. It is
Yeah.
violently scrambled. It's, chaotic. But it is not gone. It is never gone.
Exactly. Now take that exact same safe, but instead of a bonfire, you drop it into a black hole.
And the universe just throws its hands in the air. I mean, the comfort of classical physics shatters completely.
Right.
Because the moment that safe crosses the event horizon, we're no longer talking about scrambled ashes or tracking smoke. We are staring down the barrel of the single greatest crisis in modern theoretical physics.
Because the information isn't just hidden. The mathematics suggest it is fundamentally deleted from reality.
Yes.
And that brings us to the core of our deep dive today. We are unpacking an incredibly dense, genuinely mind-bending text called Physics of Black Holes, a guided tour.
It is a phenomenal source.
It really is. And this text argues that this exact scenario, tossing our metaphorical safe into the abyss, forces us to confront two massive, universe-breaking mysteries.
Mysteries that sit precisely on the razor's edge, where the rules of the very small quantum mechanics crash violently into the rules of the very heavy general relativity.
Right. So we are looking at the information paradox, which is what actually happens to the fabric of reality when stuff falls in.
And we're also looking at the no-hair conjecture, which asks if black holes are just simple featureless spheres, or if they can harbor incredibly complex observable features on their surface.
So why should you care about this? Well, the stakes here are absolute.
Completely. We aren't just arguing over the taxonomy of some exotic, distant space phenomena, right? Solving these paradoxes is the master key to understanding the fundamental nature of reality itself.
Black holes are the ultimate stress test.
Exactly. If our current laws of physics cannot explain what happens to that safe inside a black hole, then our laws of physics are incomplete. They are flawed at the foundational level.
I mean, I'm trying to picture this. The safe goes in the event horizon, which is the boundary where gravity is so strong that not even light can escape. It just swallows it. My immediate thought is, isn't the information just, well, inside? Why are physicists tearing their hair out over what is essentially a cosmic trash can with a one-way lid?
It sounds simple, right?
Yeah, like if I throw my tax returns into a trash can, I don't trigger a crisis in physics. The trash is just in the can.
You'd think so, but the problem starts with the thermodynamic ledger of the universe.
The ledger.
Yeah. To understand why the trash can analogy fails, we have to look at the second law of thermodynamics.
Which is arguably the most untouchable rule in physics.
Without a doubt. It states that the total entropy of an isolated system, and ultimately the universe itself, must always increase, or at least stay the same over time.
So things must naturally progress from a state of order to a state of disorder.
Exactly.
Yeah.
You can break an egg, but you can't spontaneously unbreak it. Entropy is a measure of that disorder. Or, more accurately, it's a measure of the hidden information in a system.
Okay, so every physical object, every box of gas, every burning safe, it has a specific amount of entropy.
Yes. Now, imagine a sealed box of gas with a measurable amount of entropy. You toss it into a classical black hole.
Okay.
According to Einstein's general relativity, the black hole is a perfect, featureless, one-way void. It has mass, it has spin, it has electrical charge, but it has no internal structure that the outside universe can ever interact with.
So from the perspective of an observer outside the black hole, that box of gas and all of its entropy has just completely vanished from the observable universe.
Right.
And if it vanished, the total entropy of the observable universe just went down, which violates the second law.
Exactly. And you don't just casually violate the second law of thermodynamics.
Right, because if the entropy of the universe can decrease just by tossing things into a black hole, you have broken the arrow of time.
You've broken the fundamental rules of heat and energy.
Yeah,
So physicists in the 1970s realized they had a massive problem.
I bet.
If the universe's thermodynamic ledger must be balanced, the black hole itself must possess its own entropy to account for the stuff falling into it.
But wait, how could a featureless void have entropy? I mean, entropy implies microscopic moving parts, different possible states, complexity. How do you measure the complexity of a bottomless pit?
It's a great question. And Jacob Bekenstein was the one who provided the breakthrough.
How did he do it?
He did it by looking at the geometry of the black hole. He realized that when our box of gas falls into the black hole, adding its mass to the singularity, the physical radius of the event horizon expands.
Right, the black hole gets physically bigger.
Yes. So Bekenstein proposed that the surface area of the event horizon isn't just a boundary. It is a direct, measurable substitute for entropy.
Wow.
He derived this beautifully simple yet terrifying equation. Bekenstein entropy, where S equals A over 4G. Entropy equals the area of the horizon divided by 4 times Newton's gravitational constant.
Meaning the black hole absolutely has its own entropy? The universe's ledger is saved?
Exactly. Safe for now.
But the text gets into the sheer, incomprehensible math of this formula, and this is where my brain starts to overheat.
It gets wild here.
Because in statistical physics, entropy isn't just an abstract concept, right? It relates directly to the number of possible microscopic arrangements a system can have, the microstates.
Yes, that is the core of statistical mechanics, pioneered by Ludwig Boltzmann. Entropy is the natural logarithm of the number of possible microscopic states.
Okay.
So, if we take Bekenstein's formula and apply it to a perfectly standard, typical black hole, say, one with the exact mass of our sun.
Which would have an event horizon radius of about 3 kilometers, right?
Roughly, yes. The mathematics tell us that this 3-kilometer sphere possesses a number of microstates equal to 10 to the power of 77.
10 to the 77th power. That is a 10 followed by 77 zeros.
It is a number so staggeringly colossal that human intuition simply cannot map it. It dwarfs the number of atoms in a star.
Oh.
It represents a density of information that is unparalleled anywhere else in the cosmos.
Okay, let's untack this. Because if I take my tax returns, which are full of very specific ordered numbers, and I throw them into a physical paper shredder.
The information is highly disordered. The entropy has increased.
Right. But the physical scraps of paper are still right there in the bin. I can see the complexity.
Sure.
But if I throw those tax returns into a black hole, Bekenstein's formula is telling us that the black hole surface area grows specifically to account for that information?
Yes, the area increases.
But where are the receipts? Are there, like, 10 to the 77 tiny little crumpled up receipts painted on the invisible surface of the event horizon? Where is this information physically residing?
Classical general relativity looks at that question and answers with a resounding nowhere.
Nowhere?
There is nowhere for it to be. The mathematics of a classical black hole explicitly forbid complexity on the event horizon.
Really?
Yeah. If you tried to deform a black hole, if you try to put a bump on it or an asymmetry or a tiny pocket of complex information, the extreme gravity ensures that it either immediately falls through the horizon into the singularity or it is aggressively radiated away in the form of gravitational waves.
So the event horizon acts like a perfectly stretched drum skin that instantly dampens any vibration.
Exactly. It rapidly settles back down into a perfectly smooth, featureless sphere.
Hence the famous phrase from physicist John Wheeler, black holes have no hair, they're completely bald.
Right. From the outside, the only properties you can ever measure are mass, angular momentum, and electric charge. 3 simple numbers.
And this is the massive contradiction at the heart of black hole thermodynamics. Statistical physics demands that the black hole must have 10 to the 77 unique microscopic states to satisfy the laws of entropy.
But general relativity demands that the black hole has exactly one state, a bald, featureless sphere defined by 3 numbers. The microstates cannot be on the surface, because the surface must be perfectly smooth.
So they have to be inside. I mean, the only logical place left for all that complex information to hide is deep down at the bottom of the gravity, well, at the singularity itself, the point of infinite density.
That's the assumption many made.
Right, because if we just assume the information is locked away in the singularity forever, then thermodynamics is saved, the no-hair theorem is preserved, and we don't have to break physics.
Right. Assuming the information is safely locked away in the singularity is exactly the trap that theoretical physics fell into for a little while.
Oh, no.
Yeah, it feels like a tidy compromise. But it sets the stage for a devastating realization.
What's the realization?
Because if Bekenstein is right and this black hole has an internal entropy, well, doesn't standard thermodynamics demand that anything with an entropy must have a temperature?
Wait, yes. If a system has entropy, it has a temperature above absolute zero. And if an object has a temperature above absolute zero, it cannot be perfectly dark. It has to radiate heat. It has to glow.
Exactly.
But we are talking about a black hole. It is defined by the fact that its gravitational pull is so immense that not even light moving at 186,000 miles per second can achieve escape velocity.
Right.
How can a trap that light cannot escape possibly radiate anything?
Answering that requires us to completely change how we view the vacuum of space.
Yeah.
Because the answer isn't classical. It is quantum.
Okay, quantum field theory.
Yes. We have to look at quantum field theory, which tells us that the vacuum of space is not a vast, empty nothingness. Empty space is actually a boiling, roiling ocean of quantum fluctuations.
I love this concept. When we picture a vacuum, we picture total emptiness.
But at the quantum level, it's chaotic. Pairs of particles specifically, a particle and its antimatter twin, like an electron and a positron, are constantly, spontaneously popping into existence out of the void.
They borrow a microscopic amount of energy from the universe, exist for an infinitesimal fraction of a second, and then immediately slam back into each other and annihilate.
Exactly. They pop in, they pop out, they cancel each other out so quickly that we can't normally see them. They are virtual particles.
Virtual particles, right. They are a mathematical certainty of the Heisenberg uncertainty principle.
Yes. Now, to understand how a black hole forces these virtual particles to become real, the source text walks us through an analogy using something called the Schwinger effect.
The Schwinger effect.
Right. Imagine you have a pure, empty vacuum in a laboratory, and you apply an unimaginably strong electric field to it.
Okay.
When an electron and a positron pair pops into existence as a quantum fluctuation, they naturally want to snap back together. But because the electron has a negative charge and the positron has a positive charge, the extreme electric field yanks them in opposite directions.
Oh, I see. It pulls them apart before they have a chance to annihilate.
Yes. If the electric field is strong enough, it provides the energy to rip the virtual pair apart. They are forced into reality. They become real, observable particles.
And you suddenly have an electric current flowing out of what was completely empty space.
Exactly. Stephen Hawking realized in 1974 that the extreme gravitational field of a black hole does the exact same thing, but using the geometry of space-time itself rather than an electric field.
Let me try to visualize this. The gravitational pull of a black hole gets stronger the closer you get to the event horizon, right?
Very much so. Space-time is literally stretching and warping.
So imagine a conveyor belt moving at the speed of light, and this conveyor belt leads straight into a pitch black room with a trap door. That's our black hole.
I like this.
Now, you have two people holding hands standing right on the edge of this conveyor belt. They pop into existence. The gravitational pull is the conveyor belt.
Okay.
Right at the horizon, the force is so extreme, and the difference in gravity over such a tiny distance is so sharp that one person gets pulled violently forward, slipping past the trapdoor and falling into the dark room.
And the other person?
The other person, who popped in just a fraction of a millimeter further out, manages to let go. The conveyor belt is moving fast, but they are just barely outside the point of no return. They turn around, and they are flung outward, away from the trapdoor, out into the light.
That is an incredibly vivid way to picture the behavior of what physicists call null geodesics peeling off the horizon.
Null geodesics.
Right. But to really grasp how this happens, the text requires us to map out the geometry mathematically. We have to slice up the space around the black hole.
Okay, let's do it.
Imagine three distinct regions. We have an outer region, let's call it S out. This is far away from the black hole, where space-time behaves normally and is relatively flat.
Flat space. Got it.
Then we have an inner region, S, deep inside the event horizon. In this region, space-time is so warped that space and time have effectively swapped roles.
Wait, what does that mean?
It means the physical direction pointing toward the singularity is literally the forward direction of time. You can no more avoid the singularity than you can avoid tomorrow.
Wow, that's terrifying. And between the flat space outside and the time warp space inside, we have the boundary.
Yes, the connecting region,
Yeah.
SCON, which encompasses the event horizon. Because there is no single universal clock that works for both the outside observer and the inside of black hole, The slices of space we draw mathematically get infinitely stretched as they cross the horizon.
Infinitely stretched.
Right. The text uses a mathematical framework called the Eikenal approximation to track how waves behave in this intensely stretching geometry.
Let's pause on the Eikenal approximation because that sounds like heavy jargon. An Eikenal relates to tracking the phase of a wave, right? Like tracing the crests and troughs of a ripple in a pond.
Exactly. Imagine a wave of light, a quantum wave mode that originates just barely outside the event horizon.
Okay.
The Eikenal approximation allows us to track the crests and troughs of this wave as it tries to escape. Because the underlying space-time is stretching so violently as time ticks forward, the wave itself is pulled like taffy.
So it's being deformed.
Massively. What starts as a wave with a microscopic subatomic wavelength near the horizon gets stretched logarithmically by the extreme gravity. By the time this wave fights its way out of the gravitational well and reaches S out far away where an astronomer might detect it, its wavelength has been stretched to be roughly the physical size of the black hole itself.
That is wild. It starts out smaller than an atom, and gravity stretches the wave until it's miles across.
Yes, and this rapid, non-uniform stretching of the space-time fabric is the exact mechanism that creates the particles out of the vacuum.
Because the violent change in the metric of space provides the energy to pull the virtual pair apart.
Correct. And the particle that falls into the S in region actually has negative energy relative to the outside universe. Because it adds negative energy to the black hole's overall mass decreases.
Which is how a black hole shrinks.
Yes. And the partner particle, the one that gets stretched and flung out into S out, has positive energy. This continuous stream of escaping positive energy particles is what we call Hawking radiation.
So the black hole is glowing, it is radiating heat, it is losing mass by swallowing negative energy, and slowly, over trillions upon trillions of years, it is evaporating.
Exactly.
Which, on the surface, sounds like a beautiful, tidy conclusion to the life cycle of a star. The black hole eats stuff, it glows, it shrinks, and eventually it just pops out of existence. The universe is cleaned up.
This is the trap.
Right. This is the exact moment where quantum mechanics hits a brick wall and shatters.
Because we have to ask what happens to the information of the safe we threw in earlier. To understand why Hawking radiation is fatal to quantum mechanics, we cannot just look at the fact that the black hole radiates. We have to look at the quantum nature of the radiation itself.
You have to look at entanglement.
We do.
Let's go back to those two particles that popped out of the vacuum holding hands. Because they were born from the exact same quantum fluctuation, they are inextricably linked. They are quantumly entangled.
Right.
Let's call the escaping particle B1, and let's call the particle that fell into the darkroom C1. The state of B1, its spin, its momentum, its quantum properties, is entirely dependent on the state of C1. They are two halves of a whole.
In the mathematical language of quantum mechanics, a system that contains all of its necessary information is called a pure state.
A pure state.
Yes.
Yeah.
If you, as an observer, have access to both B1 and C1, you possess a pure state. You can calculate everything about them with absolute deterministic certainty.
But the problem is, you are an astronomer floating in S out. You only ever get to see B1, the Hawking radiation hitting your telescope. The partner, C1, is trapped forever inside the event horizon.
Exactly.
So if I only have half of an entangled pair mathematically, what am I looking at?
You are looking at what physicists call a mixed state.
A mixed state.
Yes, a mixed state is essentially a statistical compromise. Because you are missing crucial information, the data locked inside the black hole, with C1, you cannot definitively know the exact state of B1.
Right, you have to use a density matrix to average out the probabilities.
Exactly. Now, in standard everyday physics, mixed states are perfectly fine. They just reflect human ignorance.
Ignorance, like not knowing something.
Right. If you lose a sock in the laundry, your sock drawer is effectively in a mixed state. The missing sock still physically exists somewhere behind the dryer. You just don't have access to it. The universe hasn't broken. You're just missing data.
But the black hole is not a washing machine. The black hole is evaporating. This is the fatal flaw.
Yes, it is.
Fast forward to the very end of the black hole's life. It has radiated away all of its mass over eons. It shrinks down to a microscopic point, and then in a final flash of energy, it evaporates completely. It is gone.
And what happens to particle C1, the one that fell in? The black hole is gone. The singularity is gone. The entire interior region of spacetime, FSN, is gone. Particle C1 is deleted from the universe.
But particle B1 is still out there. It's been traveling through the cosmos for trillions of years.
Exactly. Particle B1 is still floating through space, and particle B1 is still quantumly entangled. But now it is entangled with absolutely nothing.
And that is the paradox. How can something be entangled with something that doesn't exist?
It's not just a paradox. It is a fundamental violation of the most sacred law of quantum mechanics, unitarity.
Unitarity.
Unitarity is the principle that information is always conserved, and that a pure quantum state must always evolve into another pure state.
It means that the past strictly determines the future, and if you have all the information, you can always calculate the past from the present.
Exactly. The mathematical framework of quantum mechanics, called the S-matrix, relies entirely on this.
But if a black hole evaporates and leaves behind a universe filled with Hawking radiation particles that are entangled with nothing, the universe has fundamentally evolved from a pure state into a permanently mixed state.
The cause and effect chain is severed. The math literally breaks down. The universe has suffered a permanent loss of memory.
So how did the physics community react to this? Because Stephen Hawking looked at this math in 1976 and essentially said, well, if the math breaks, the math breaks.
Good.
He famously proposed that we just have to throw away standard quantum mechanics when gravity gets involved.
Yeah.
He suggested tossing out the predictable S-matrix and replacing it with something he jokingly called the dollar matrix.
The dollar matrix, yes.
A mathematical framework where information just fundamentally, inherently leaks out of the universe and is lost forever.
Hawking's proposal sent absolute shockwaves through the theoretical physics community. It triggered a decades-long intellectual war, most famously between Hawking and physicists like Leonard Susskind and John Preskill.
Because most physicists were violently unwilling to abandon unitarity.
Of course. Quantum mechanics is the most rigorously tested, empirically successful framework in the history of human science. It works flawlessly to describe lasers, microchips, chemistry, and stars. Why should we throw the foundational rules of reality in the garbage just because black holes behave weirdly?
Let me push back on this, because there is a very intuitive counter-argument laid out in the source text that I think a lot of people would naturally wonder about.
I'll hear it.
Let's go back to our safe in the bonfire, or, as the text simplifies it, a burning piece of coal. If I set a piece of coal on fire, it turns to ash, and the smoke and heat radiate away. To a human observer, that heat radiation looks completely random. It is thermal. It looks exactly like a mixed state. Isn't that exactly what the black hole is doing? It's just radiating thermal heat. Why doesn't a burning piece of coal break quantum mechanics? What makes the black hole's radiation so uniquely destructive to physics?
That is the exact right question to ask. And the difference illuminates the profound strangeness of black hole geometry. It all comes down to causal contact.
Causal contact, okay.
When a piece of coal burns, an atom on the surface of the coal gets excited and emits a photon of light. That atom doesn't vanish. It's still sitting there in the coal, vibrating, entangled with the photon it just emitted.
Right.
A tiny fraction of a second later, the next atom emits a photon.
Right.
Crucially, before that second photon escapes, it can interact with the first atom. It can bounce off it. The atoms left behind in the burning coal are in constant, ongoing causal contact with the new radiation being produced.
Oh, so they are constantly whispering to each other.
Exactly. Because of these micro-interactions, the information about the coal's internal structure is subtly and complexly imprinted into the correlations between all the outgoing photons. The information bounces around, and it leaves with the smoke. It's
incredibly difficult to decode. You'd need that supercomputer we talked about, but the math proves it is a pure state. The information gets out.
Yes. But the black hole is fundamentally different because of the geometry we mapped out earlier. The event horizon ruins the whispering.
How so?
Remember how the S in region, the space inside the horizon, behaves? The spatial slices inside are infinitely stretching towards the singularity.
Right.
When our first particle, C1, falls into the black hole, it is immediately grabbed by this stretching space and swept violently inward. When the black hole emits the next Hawking particle, C2, just a fraction of a second later, C1 is already gone. It has been carried away on an infinitely elongating spatial slice.
Because space inside is stretching faster than light, C1 is spatially separated from the horizon. It can never, ever interact with the creation of C2. They are physically forbidden from bumping into each other. They cannot share information.
Precisely. The early matter that falls in is completely causally disconnected from the radiation that is emitted later. They are in two separate realities.
Wow.
Therefore, the Hawking radiation that comes out cannot carry any of the original information of the safe, or the box of gas, or the early particles. The radiation is entirely blind to what is happening deep inside the hole.
Which leads directly to what the text calls Hawking's theorem. It's not just a guess, it's a brutal, mathematically rigorous theorem.
Yes.
Hawking proved that if you accept two specific assumptions about the universe, information loss isn't just a possibility, it is an absolute, unavoidable mathematical certainty.
Those two assumptions are the linchpins of the entire paradox. First, you must assume that the vacuum of space is unique, that empty space is just standard empty space everywhere.
And the
Second, and crucially, you assume that the effects of quantum gravity only operate at the absolute smallest scale imaginable, the Planck length.
The Planck length. That's the scale where the fabric of spacetime itself becomes quantized and foamy. It's something like 10 to the negative 33rd centimeters. It is so incomprehensibly tiny that a proton is gargantuan by comparison.
Right. Hawking's theorem says that if quantum gravity only kicks in when matter is crushed down to the Planck length, which only happens at the exact center of the black hole, at the singularity, then the event horizon itself is just normal, low-curvature empty space.
I see.
And in normal empty space, quantum field theory proves exactly what we just discussed. The virtual particles separate, the radiation is entangled with the partner falls into the singularity, the whole evaporates, and the information is irrecoverably lost. Period. The math is ironclad.
So if you are a physicist who refuses to let quantum mechanics die, you can't just tweak the math around the edges.
No, Hawking's logic is too sound.
You have to take a sledgehammer to one of his two core assumptions. You have to prove that quantum gravity doesn't just sit quietly at the Planck scale. You have to prove Hawking fundamentally wrong about the nature of space.
Which is exactly what a massive faction of theoretical physicists set out to do. They needed a mechanism to bring quantum gravity out of the microscopic depths of the singularity and spread it all the way out to the event horizon.
And that brings us to the cavalry coming over the hill, string theory's rescue.
String theory, yes.
The framework that suggests the fundamental ingredients of the universe aren't tiny zero-dimensional dots or particles, but incredibly small, one-dimensional, vibrating loops of string. Different vibrations create different particles, like different notes on a violin string.
That's the basic idea.
I love how the text dives into this, because to save quantum mechanics, string theorists couldn't just look at a collapsed star. They had to mathematically build a black hole from scratch, using the fundamental objects of their theory.
Yes, and to do that, you have to embrace the multidimensional math of string theory. The text references the construction of black holes in compactified dimensions.
Compactified dimensions, right.
String theory mathematically requires the universe to have more dimensions than the three spatial dimensions and one time dimension we experience. The math only balances if there are hidden dimensions, but they are curled up, compactified into microscopic loops and spheres, often represented mathematically as toruses.
Like looking at a garden hose from far away, it looks like a 1D line. But if you zoom in, you see it actually has a 2D surface wrapped around it in a circle. The extra dimension is there, it's just tiny.
Exactly. So string theorists build a black hole by taking fundamental strings and multidimensional membranes called branes and wrapping them tightly around these microscopic curled up dimensions.
Okay.
Now, if you take a single isolated fundamental string and wrap it around a compact dimension, it possesses an immense amount of intrinsic tension.
It's pulled taut.
Highly taut. Because of this extreme tension, the string naturally wants to minimize its length. It shrinks down, pulling itself into the absolute smallest possible size, which is exactly the Planck length.
Okay, so if we stop there, string theory perfectly agrees with Hawking's assumption. The fundamental stuff shrinks down to a tiny dot at the singularity. Quantum gravity stays microscopic. The paradox survives.
It would, yes.
But the text introduces a mechanism that changes everything. Fractionation.
Fractionation is the magic bullet.
How does it work?
Well, what happens when you don't just have one string, but you take a colossal number of these strings and branes and bind them all together to build the mass of a black hole?
You would intuitively think that binding more strings together just creates a heavier, denser, tiny dot.
But string theory reveals that when you bind these objects together, they share their energy. And when they share their energy, the fundamental tension of the entire bound structure drastically drops.
Let me try an analogy to conceptualize this tension drop,
Yeah.
because it's vital. Imagine you have a very thick, heavy-duty rubber band. If you pull it, it requires a lot of force, and it snaps back instantly. It aggressively wants to be small.
Right.
That is a single string with high tension. But now, imagine you link a billion of these rubber bands together, weaving them into a massive tangled chain.
Okay.
The overall structure isn't just a tiny, tight knot anymore. The tension is distributed across a billion links. The structure becomes loose, it becomes floppy, it loses that aggressive drive to stay microscopic.
Floppy is a remarkably accurate way to picture it. Because the tension drops so dramatically through fractionation, this massive bound state of strings can no longer sit quietly as an infinitesimally tiny point at the singularity.
Because they're floppy.
Right. The strings are inherently vibrating, they possess quantum fluctuations, transverse oscillations, and because the tension is now so low, those continuous vibrations cause the entire tangled mass of strings to expand outward.
It fluffs up, but outward, like how far? Because this is the crux of the whole debate.
This is where the math provides a breathtaking revelation. When string theorists calculate the physical size of this expanding, vibrating, low-tension bound state of strings, the radius it expands to is exactly, perfectly equal to the radius of the classical event horizon.
Wait, really? It's not a coincidence. It matches exactly.
It is not a coincidence. The mass of the strings dictates the gravity, which dictates the theoretical horizon, and the fractional tension dictates the physical expansion of the strings. Mathematics converge perfectly. The boundary of this expanding mass of strings is the size of the event horizon.
So think about what this means. We have spent decades picturing a black hole as an empty room with a trapdoor in the middle. The event horizon was just a mathematical boundary, an invisible line in empty space, and all the mass was crushed down at the trapdoor.
That was the classical view.
But string theory is asserting that the room isn't empty. The room is completely physically full. It is a giant cosmic ball of vibrating yarn.
Yes. The term coined by physicist Samir Mathur is the fuzzball. The horizon is an illusion. There is no empty space inside the event horizon.
There's no infinitely stretching S in region.
Exactly. The entire interior of the black hole is filled to the brim with a dense, highly complex, vibrating web of quantum strings.
That fundamentally rewrites the entire paradox.
Yeah.
If the black hole is a solid, a dense, stringy, solid-ish mass, then when we throw our safe in, it doesn't just fall through empty space and vanish into a disconnected singularity. It hits the fuzzball.
Exactly. When matter falls into a fuzzball, it impacts this dense web of strings. The strings absorb the mass and energy of the safe, they vibrate, they reconfigure.
And the information of the safe, every atom, every ink molecule is physical energy, and it is imprinted directly onto the complex quantum vibrations of the entire fuzzball structure.
And because the fuzzball extends all the way out to the edge of the black hole, there is no infinitely stretching void separating the inside from the outside.
You've hit the exact mechanism that saves physics. Because the fuzzball's physical structure reaches the horizon, it interacts directly with the quantum fluctuations happening there. The Hawking radiation isn't being created in empty space. It is being emitted directly by the vibrating strings of the fuzzball themselves.
And just like the atoms in our burning piece of coal, those vibrating strings are in constant, continuous causal contact with each other.
They are whispering. The information is bouncing around the strings, and as the strings radiate heat, the information is encoded into the outgoing radiation.
Precisely. The Hawking radiation is no longer entangled with an isolated particle falling into a disconnected void. It is entangled with the complex, vibrating surface of the fuzzball.
The radiation encodes the information. The cause and effect chain is unbroken. The S matrix is saved.
By proving that the effects of quantum gravity don't stay trapped at the microscopic Planck lengths, but actually scale up to the macroscopic size of the entire black hole, string theory shatters Hawking's core assumption.
The fuzzball theory demonstrates that information is perfectly preserved and radiated back out. The universe doesn't delete files. The universe remembers.
It is an incredibly elegant solution to the information paradox. String theory provides the black hole with 10 to the 77 unique microscopic states by calculating the near infinite number of ways you can arrange and vibrate that giant ball of string.
The microstates aren't hiding at the singularity. They are the physical structure of the fuzzball itself.
Exactly.
I love that. The universe remembers. Okay, so we've spent a lot of time down in the quantum trenches. String theory gives the black hole these incredibly complex quantum properties on the inside.
Yes, the inside.
But I want to zoom out. Let's step back from strings and quantum entanglement and look at the black hole through the lens of classical astrophysics again. Let's revisit the outside surface.
Let's do it.
Because the text guides us through an equally fascinating loophole in classical physics. We established earlier that in classical general relativity, black holes are totally bald. Mass, spin, charge, no complex features, no hair.
Right. The classical no-hair theorems, rigorously proven by physicists like Werner Israel and Brandon Carter, demonstrated that you cannot have a black hole with complex, observable features on its surface.
And this is but those theorems were proven using a specific set of rules, right?
Yes, they only calculated the interactions between gravity and electromagnetism.
Electromagnetism being the force of light and magnets.
Yes. In the language of physics, electromagnetism is described by an abelian gauge field. The math of an abelian field is relatively straightforward and linear, primarily because the particles that carry the electromagnetic force, photons, do not interact with each other.
You can shine two flashlights at each other and the beams of light pass right through each other like ghosts. They don't crash and bounce.
They are polite particles.
They are polite particles. But the text asks a vital question. What happens if we drop a non-abelian gauge field into the math of the black hole?
And that changes the entire landscape. A perfect example of a non-abelian gauge field is the strong nuclear force, the fundamental force that binds quarks together to form protons and holds the nucleus of an atom together.
And the particles that carry the strong force are called gluons.
Unlike photons, gluons carry a charge themselves. This means gluons aggressively interact with each other. They trash, they pull, they exchange charge, they create a chaotic, self-interfering soup.
They are not polite, they are messy.
Incredibly messy. Mathematically, this self-interaction makes the equations highly nonlinear and phenomenally complicated. The equations that describe these non-abelian fields are called Yang-Mills equations.
So theoretical physicists ask, what happens when you combine Einstein's equations of gravity with the Yang-Mills equations of the strong nuclear force?
You get a framework called Einstein-Yang-Mills theory, or EYM.
And when you run the mathematics of a black hole using EYM theory instead of just polite electromagnetism, the classical rules break.
They completely shatter. In the late 1980s and early 1990s, with the advent of powerful supercomputers, physicists began running numerical simulations of EYM black holes.
And what did they find?
They discovered solutions that explicitly violated Israel's theorem.
Israel's theorem stated that static black holes that aren't spinning must be perfectly, flawlessly spherical.
Right. But the EYM simulations revealed mathematically valid static black holes that were axisymmetric.
Axisymmetric, meaning they are symmetrical around a central axis, like a spinning top or a slightly squashed pumpkin, rather than a perfect billiard ball.
Yes. They had features. They had a complex gauge field enveloping them. They had hair.
The mathematics proved that classical hair was theoretically possible if you introduced non-abelian fields.
Exactly.
But wait. If the math of the strong nuclear force says these hairy, squashed, complex black holes can exist, why aren't astronomers seeing them everywhere? If a black hole can have complex, non-spherical shapes on the outside, why do we still teach in universities that they are bald?
Because the mathematics also revealed a fatal flaw in these hairy black holes. The instability problem.
Instability.
You have to remember the assumed environment we were placing these black holes into. The classical no-hair theorems and the initial EYM simulations all assume an environment of asymptotically flat space.
Asymptotically flat space, meaning that if you travel far enough away from the black hole, the gravitational warping fades away and space-time levels out into a flat, empty, standard universe.
Right. Like placing a bowling ball on a massive trampoline right next to the ball, the fabric dips heavily, but 20 feet away, the trampoline is basically flat.
Exactly.
And when you analyze the physics of these hairy EYM black holes in an asymptotically flat universe, you find that they're inherently, fundamentally unstable.
Unstable how?
The hair, the complex non-spherical gauge field outside the horizon, is the result of an incredibly delicate balancing act. The massive inward pull of the black hole's gravity is fighting against the outward repulsive pressure of the interacting Yang-Mills gauge fields.
It's a tug of war. Let me try an analogy. Imagine taking a highly pressurized balloon representing the outward Yang-Mills pressure and squeezing it inside a rigid metal sphere representing the inward crush of gravity.
Okay.
If the sphere is absolutely perfect, the balloon is trapped, it's balanced. But if there is even a microscopic hairline crack in that metal sphere,
The balance is violently broken. Yes.
that hairline crack is what physicists call a perturbation.
Right. In the real universe, nothing sits in perfect isolation. A hairy black hole in flat space will eventually be hit by a stray photon or a tiny gravitational wave from a distant star, or even a microscopic quantum fluctuation.
And the instant that perturbation hits, the delicate balance between gravity and the gauge field shatters. the black hole violently loses its
And
equilibrium.
the balloon bursts.
It either explodes outward, violently radiating its Yang-Mills hair away into deep space, or it collapses inward, swallowing the complex gauge fields entirely behind the event horizon.
And what is left behind after the explosion or the collapse?
A completely standard, perfectly bald, featureless Schwarzschild black hole. The hair is gone.
So while the strict letter of the no-hair theorem was technically violated because the math allows for these complex states to momentarily exist, the spirit of the no-hair theorem survives perfectly in flat space.
Hairy black holes might form, but they quickly shed their hair and settle down into bald simplicity. The stable end state of a black hole in our universe is still simple.
Exactly.
Okay, so in our normal, flat universe, hair is a fleeting instability. But, well, theoretical physics isn't confined to our normal universe. What if we change the container?
Now we're getting to the fun part.
What if we take this delicate, unstable, hairy black hole and we place it in a completely different kind of spacetime? This brings us to the final and frankly most mind-bending part of the text, the infinite hair of anti-de Sitter space.
Now we are entering a profoundly strange, highly abstract theoretical playground. To change the container, we change the overarching geometry of the entire universe by introducing something called a negative cosmological constant.
Let's break that down. A cosmological constant is essentially the background energy density of the vacuum of space itself. Our actual observed universe has a positive cosmological constant, which acts like a repulsive force.
Right. It is the dark energy that makes our universe expand and accelerate outward.
So a negative cosmological constant does the exact opposite. It provides a constant, overarching inward pull. It makes the universe curve inward on itself, creating a highly specific geometry known as anti-de Sitter space, or ADS space.
The easiest way to conceptualize ADS space is to imagine a universe that functions like a giant reflective box.
A reflective box.
In our flat universe, if you shine a laser pointer out into the void, that beam of light will travel in a straight line infinitely forever. But in ADS space, because of the extreme inward curvature caused by the negative cosmological constant, that laser beam will eventually reach the mathematical boundary of the universe, and the geometry will bend the light entirely around, bouncing it back toward you.
It is a universe with a built-in infinite containment field. Okay, so we take our delicate pressurized balloon inside a cracked sphere, hairy black hole, and we drop it inside this reflective 8S box. We run the EYM math again. What happens?
The solutions completely transform. In flat space, the math only allowed for discrete, highly specific, fragile states of hair. But in 8S space, using the simplest version of EYM theory, which is based on a gauge group called SU2, we suddenly find continuous open intervals of mathematical solutions.
The restrictions vanish. The math opens up.
Yes.
But the big question is the stability. Does it still explode?
This is the breakthrough. The text details how physicists analyze stability by breaking down the equations of perturbation, the little cracks in the sphere, into two mathematical sectors.
What are they?
The spheroronic sector, which tracks the fluctuations of the Yang-Mills gauge fields, and the gravitational sector, which tracks the ripples in the spacetime metric.
Okay.
When you run these perturbation calculations in 8S space, you find that the instability completely vanishes. The hair is no longer fragile, it becomes rock solid, it is completely stable.
Wow. How? Why does putting it in a curved box suddenly stabilize this incredibly chaotic dynamic?
Because the negative cosmological constant of the ADS space provides a continuous, overarching inward pressure from the curvature of the universe itself.
It acts like an invisible scaffolding that perfectly supports the delicate balance between the black hole's gravity and the outward pressure of the Yang-Mills gauge fields.
The balloon doesn't burst out of the cracked sphere because the sheer pressure of the surrounding room is pushing back, holding everything perfectly in place.
That is incredible. The environment stabilizes the anomaly, but the text doesn't stop at SU2. It takes it a step further into absolute absurdity.
Oh, it really does.
Because SU2 is just the simplest non-abelian model. What if we use a much larger, much more complex stage group? What if we calculate for SU, where n can be any arbitrarily large number of interacting fields?
Then the mathematical possibilities literally explode into infinity. The text highlights a relatively recent mathematical proof, specifically Ruan's proof for the SU gauge group.
What does that prove?
This proof demonstrates that in ADS space, you aren't just limited to a few stable hairy configurations. There are infinitely many stable solutions. They are mathematically indexed by the microscopic zeros of multiple overlapping gauge functions.
Think about the journey we have taken here. We started this deep dive with the absolute textbook certainty that black holes have no hair. They are totally bald, simple, featureless spheres defined by three numbers.
Right.
Then we found that, well, maybe they have hair if you use strong nuclear forces, but it's wildly unstable and disappears instantly. And now we find out that if you simply alter the geometry of the universe it lives in, a black hole could potentially store an infinite amount of complex, stable, mathematically observable information right on its surface.
Yes. There is theoretically no mathematical limit to how much stable hair an ADS black hole can possess.
None at all.
None. You can endlessly add more and more complex Yang-Mills gauge fields, piling layers of non-abelian complexity onto the event horizon, and the overarching negative curvature of the ADS space will just hold it all together in perfect stability.
It fundamentally rewrites the identity of what a black hole is. It evolves from being the simplest, most featureless object in the universe to potentially the most infinitely complex, data-rich object imaginable.
And if we step back and connect this mathematical revelation to the broader philosophical picture of physics, it demonstrates a profound, unsettling truth.
Which is?
The fundamental nature of an object, its complexity, its stability, its capability to hold information, its very identity, is not just an intrinsic, isolated property of the object itself. It is fundamentally, inextricably dictated by the macro environment it resides in. The shape of the universe literally dictates the nature of the black hole within it.
That is just staggering. And it is the perfect place to pause and summarize the incredible reality-bending journey we've just taken through this text.
It's been quite a ride.
We started by throwing a safe full of secrets into the abyss, forcing us to confront the mind-bending nightmare of the information paradox. We mapped out how the infinitely stretching space inside a classical black hole breaks the causal contact of quantum entanglement, creating Hawking radiation that is entangled with nothing, threatening to permanently destroy the laws of physics and the universe's memory.
But
Then we discovered how string theory rides to the rescue with fuzzballs, proving that when you bind enough fundamental strings together, their tension drops, allowing them to expand and physically fill the entire event horizon, creating a complex, vibrating surface that catches information, whispers it among the strings, and radiates it safely back into the cosmos.
saving quantum mechanics.
Exactly. And finally, we zoomed out to the classical no-hair conjecture, exploring how chaotic Einstein-Yang-Mills fields can create hairy, asymmetrical black holes that explode in our flat universe, but can grow infinite, perfectly stable, complex hair if you simply place them in the reflective, negatively curved box of anti-de Sitter space.
And you, listening to this, might be asking the ultimate question: why should you care? Why does all this high-level, abstract, theoretical mathematics matter to anyone outside of a university physics department?
Why does it matter?
You should care, because black holes are not just cosmic garbage disposals or dead ends in space. They are the supreme testing ground for the rules of our reality. They are the crucibles where our understanding of physics is pushed to the absolute breaking point.
Because understanding how a black hole deals with information requires us to completely rethink the fundamental fabric of space, time, causality, and reality itself.
As the mathematics have shown us today, the universe is vastly more interconnected, vastly more complex, and vastly less empty than our classical eyes perceive.
I want to leave you with a final provocative thought to mull over, something that builds on everything we've unpacked today but takes it out of the realm of astrophysics. Think about the two brilliant solutions we found to our cosmic paradoxes. In string theory, the fuzzball saves the information of the universe because tiny, microscopic, hidden higher dimensions expand outward to create the black hole's mass and complex surface. The microscopic fundamentally creates and sustains the macroscopic.
Yeah.
But conversely, in Einstein-Yang-Mills theory, the hairy black hole only becomes stable and complex because of the overarching massive curvature of the entire universe, the macroscopic ADS space pushing inward to support it. The macroscopic container dictates the microscopic truth of the object.
So they mirror each other.
Exactly. So, what if the apparent simplicity or complexity of anything you interact with in your daily life, a person, a complex ecosystem, a persistent societal problem, a seemingly simple object, is not an intrinsic property of the thing itself?
What if complexity is simply an illusion, entirely dictated by the shape, the scale, and the curvature of the container you are observing it in?
If you completely change the container, if you step out of flat space and look at it through a different geometry, do you fundamentally change the truth of the object?
It makes you wonder just how much complex hair the mundane objects and situations in our daily lives are hiding, simply because our flat standard viewpoint refuses to let us see the underlying geometry.
Keep questioning the container. A massive thank you to everyone for joining us on this deep dive into the physics of black holes. Until next time.